Thank you. Last February, when I was sending my submission of the talk, it was easy, just some abstract and then hit submit. I never thought the possibility of the talk would be accepted. And then I was like, okay, I need to get the visa now, and then I need to travel to London, etc. It was all exciting. And the visa was declined once, so I was like, okay, should I reapply again, or should I just leave it, not come here at all? But here I am, and signal processing is something I got very excited after coming back to Mongolia from US, and then my full-time job is data scientist at an international mining company. It's a subsidiary of Rio Tinto, and since joining Rio Tinto subsidiary in Mongolia, I started working on sensor data, and then I started getting excited about it. So that's how I submitted my talk, from noisy sensor data to detecting events. And without deep learning models or neural networks, I tried to get a robust event detection with Kalman filters and hidden Markov models. So let's start with, so first of all, when I was doing master's in the US, mostly they teach about this tabular data. And data analysts, they mostly work on tabular data like future engineering, etc. But sensor data is something very different. Like, you have to rely on timestamps, and you have to format them a lot. And sometimes you make some mistakes on the timestamps that mess up whole values in there. So this is one of the very simple time series data. As you see, like at the bottom part, when it's stable, kind of stable, sensor is sending all those noisy data. And then when it's going up or when it's going down, it's very quick in a matter of a few seconds, but it's happening like. So if you look at the nature of the data, like when it's oscillating or fluctuating like that, how would you detect an event? Like when you see it with your eyes, it's easy to see it's going up, or it's easy to see when it's going down. So when you visualize the raw data, it's very easy. But the solution we are trying to get is, without looking at the data, we have to come up with an algorithm that detects the event, so that some kind of very easy to understand fact table is going into the database. So why time series data is very difficult? Although this previous one was one of the very simple sensor data, like usually they are very messy, like always fluctuating. Sometimes they are just out of range, below than zero, or out of normal range of values. So in real life, spatially sensors, they throw you off a lot. Like there is a data shift, sometimes there is no signal at all, although the event is happening, meanwhile sensor is off. And then you have to think all those things. And also sensors goes off the calibration. So you have to detect those out of calibration events too. So this is also one of the messy noisy data, which is EEG, electroencephalogram. This is where I got very interested in this data, and then trying to figure out how to process this one also, which is actually, I got interested in neurotech startup because of the signal processing. So going back to this very simple sensor data. So this is actually a sample data from weightometer sensor. So when it's around 75K, the truck has no load. It's just traveling from point A to point B. And then when it's loading, it's getting payload. And then with the payload, it's going from point B to point A back, and then it's fluctuating again, and then it's unloading the payload. You see unloading happening in the second part in here. So going back, when I got the task that I need to process this data, I started with the data distribution. And if you look at the data distribution, it's very easy that around 80K, the truck is empty. Around 150K, it's in the middle of loading phase. And around 225K, it's fully loaded. But you don't know exactly which one is the accurate or correct actual payload of the sensor. So the other business end units are just assuming that 220K is the final payload of the final tonnage of the payload. That's what we have to assume actual load. But if you look at the real payload, it could be different. So at first I started with manual processing. And from this data distribution, well, you already guessed it, I guess. The first part, around 800K, is empty state. And middle part is about loading or half-loaded state. And then the final part, around 220K, is fully loaded part. So that's, in the manual processing, that's where I defined the states, empty, half, and loaded. And also, I defined the cycle from point A to point B, loading activity, and then from point A back to from point B to back to point A, it's one cycle going fully, one full cycle. So it's from empty, half loaded, or from from loaded to empty. So we have to count each cycle, and with each cycle, we have to determine the actual tonnage of the truck. So this was my manual processing part, sorting by the date time, and like I said before, removing duplicate rows, because sensors give you the same timestamps, two different values, so you have to determine which one is the correct value or which one you need to remove automatically from the data. So removing duplicate row was also a challenge, like, do you want to remove the first row or do you want to remove the last row? So that's kind of like you have to discuss it with the business end users, like which one do you accept if the timestamps are same. And also we need to remove those unlikely outlier values, like if the sensor is detecting less than 0 value, which shouldn't happen because it's weightometer data. And when the maximum payload is 250K, if sensor is detecting more than 250K, sometimes around 500K, then would you accept it or not? So coming back to the algorithm, at first I assigned IDs to the date times, and then I assigned states to the rows, and then I tried to remove weight noise. And then the cycle determining part is coming up. So if the rows have same state, at first I flagged rows that have changed the state. So one row is empty, it's going on with empty, 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 and then when the payload is coming up, when it reaches to the threshold point of half-loaded, its state is changing to half-loaded. So that's where you flag the state changing is happening. Then find average weight for that state, because for empty you have many rows, you just average it out, and then add use those columns to define the cycle. But and also with this algorithm, we got this kind of flaw from sensor system. At first, you log all the data, raw data, into a database, and then with my algorithm, first step is removing noise, and then second step is state definition, also cycle definition. Put it, store it back into the database, and then dashboard, like how many cycles the truck did for the day, or how many payloads was carried for the day. So that kind of dashboard was built from this automated processing. But you see here, all this processing was actually only just 2 big steps. One is noise removal, and then the other one is state definition. And also with the dashboards, actually business users complain that my numbers are, not my, algorithm numbers are different than the actual numbers. Like they said roughly 10% change is detected. So I have to change it, or they have to accept that it's weightometer actual tonnage. So I started digging. That's where I figured out Kalman filter is something used for noise removal. So there are, I found 4 different noise removal techniques. The very easy one we were taught at school is moving average. Like consecutive 10 numbers are averaged to find the total tonnage, or like you can play with that number when you're calculating moving average, like 5 consecutive numbers or 10 consecutive. It doesn't matter, it's just moving average. And there were 2 other methods like Savitsky or something like that. But with sensor data, Kalman filter worked best. The very simple idea about the Kalman filter is at first it's just predicting one number. And then when the next number comes up, Kalman filter is actually fixing its own Kalman gain parameter and then applying it to the next estimate. So if you look at the predict and update part, you will see that it's always predicting next state, updating its parameters, and then predicting the next state. So this one works very well with the continuous data. So continuous data means it perfectly works well with that weightometer sensor data. So it's about that Kalman filter thing. First of all, prediction. Filter predicts next state of the system based on the previous state. And then the updating part is actual sensor measurement is used for changing the parameter, and then it corrects its filter. So if you refer back to the image, you see that it's almost like linear regression correction is happening there. So I visualized how Kalman filter is working with the moving average. If you look at the moving average, the average of that fluctuation part, even though it's a little bit less than the actual fluctuation, there is still some fluctuation going on with the moving average. Like it did not matter how much I increased the number. 10, 20, or something. There was always some kind of fluctuation. But with the Kalman filter, it was much more smoother than the actual numbers. So, and also, if you notice the yellow lines here, it's actually estimating very well when the sensor is not available. Sensor data is not available. So when sensor is out, so like with the next value from the sensor, it's actually predicting very well the values should have been if the sensor was on. So this is comparison between Kalman filter and moving average. So I think you have seen from here the benefits of the Kalman filter. First of all, it's accuracy because it's always updating the parameters. Accuracy is very good, and adaptability, as we have shown in this image, when there is no sensor value, it's trying to predict the value when it's off. And then efficiency. Oh, efficiency is a very nice thing, because when you have real data and then when the sensor is logging like every second, then it should calculate the next one quickly and then have to log into or use the value for the next estimation. So this is part of the code, just to show it here. The first part is Kalman filter class. It's just the initiation in the instance creation. You see that process variance, measurement variance, estimate, and error covariance. 4 parameters are initiated. And then predict is just returning estimate, but it's also updating error covariance, Kalman gain, and then updating its estimate again. So the real job is happening in that update part. Kalman gain parameter is getting updated with each error covariance is updated. So Kalman gain is where Kalman filter is saying that, okay, we are accepting this estimate, or we are not accepting this estimate, or what percentage of the actual value or what percentage of the estimate we are using it. So this is what I used for the Kalman. This is what I used for the weight here, that real actual weight of the sensor. So if we refer back to this flow, the second step was state definition. So state definition is trying to figure out if the if the step is loading or unloading. That's where Hidden Markov Model is coming up. Hidden Markov Model, I think you have all heard of Markov chain. It's like states, you transition from one state to the next state. It's derived from that. Hidden Markov Model is actually a model that represents hidden states. So in the Hidden Markov Model, we have states, obviously, and observations on those states, and then transition probabilities and emission probabilities. But if you look at this picture, it will make more sense. So by hidden state, what do we mean is we can't always see the state of the system, but we see the observations For example, in this case, the example is we can't see the weather because we are at home maybe. We can't see outside. But we see people are carrying umbrellas. That's the observation. So if someone is carrying an umbrella, we assume that it's raining. So we also take our umbrella. That's the very natural intuition of this hidden Markov model. But also states should be transitioning from one to another with certain probabilities. Like if it's raining today, what's the probability of raining tomorrow? Or if it's sunny today, what's the probability of raining tomorrow? So what's the advantages of hidden Markov model for event detection in sensor data? It works very well with the sequential data handling and then state estimation. Hidden Markov model estimates hidden state of the system based on the observed data, and then probabilistic nature of the model, and then flexibility. It's like it can work on different types of sensor data. But let me quickly move forward and then show this visualization. This is a sleep stage visualization. Like if you see the image, when we are sleeping, at first NREM stage is happening and then REM stage is happening. When we are sleeping, of course, we don't know which stage our brain is. So that's where hidden state is really mentioning. But observation in this case is, for example, those EEG sensors, when it's put on our head, it measures all those electric activities in our head. So that's our observation is happening. So each time some kind of wave is measured by the EEG, we can say that, okay, NREM is happening now, or REM is happening now. So these two images actually very real data of the sleep stages. So you see from wake to N1, N2, N3, and then REM stages. So this is one of the cases where hidden Markov model works very well too. So let me go back. So these are the advantages of hidden Markov model. It works very well with the sequential data handling, which is sensor data is all about transitioning from one system to another, one state to another state. So with our simple example, it's just loaded or unloaded state. It's happening from one of the state to next state, which works well with the hidden Markov model. And also, unlike the Kalman filter, you have to train first the model. Training is easy. It's just using a class and then using your original data, and then using predicting the next one is just using that model, which is the easy part. So with our simple example, this is what the state prediction is visualized like this. So 0 with the blue, it's actually loaded state. And then 1 is actually unloaded state. And if you see the image, the top images with the very cleaned, smoothed out data, sensor data. The bottom image is raw data. And actually, you can see that when it's going very high, like much above the 100K, the loading state is triggered. And then when it's going down, actually unloading is happening. It's detecting unloading event very early than around like 160K. So this is how it's visualized when the code algorithm was working. And before I said event detection or activity recognition works very well with the hidden Markov model. And also I saw that failure prediction and situational awareness, those cases are also very good at good with the hidden Markov model. So it seems like Kalman filter and hidden Markov models are very similar algorithms or models. Like both of them is working the next state or next value of the sensor data. So what's the difference between them? Difference is Kalman filter works on continuous value, but hidden Markov model works on discrete value. And examples I have already mentioned, like Kalman filter is weightometer, position, or velocity. Those types of value works with the Kalman filter. On the other side, hidden Markov model works with the discrete stages, like that sleep stage. And then with the Kalman filter, the noise is almost defined by Gaussian noise. And in the hidden Markov model, the residue is just the observation. And for the Kalman filter, we don't need pre-training, but hidden Markov model, we need a small training on the historical data. So this is the result, comparing to the manual processing of the sensor data, and then comparing it with new algorithm. I mean, what I mean is Kalman filter with the hidden Markov model. So the tonnage difference with the new model, new algorithm is around 0. Median is the 0. And then the old algorithm, if you see the box plot, median is higher than 0, and then it's going way up to 4K. And in terms of percentage-wise, like how closely the new algorithm is detecting the actual value, it's actually a new one is 100%, around 100% it's detecting the actual value, but the old manual processing is like median is something around 20% different. So actually, when business users told me that there is 10% difference, they were not telling me the truth. It was actually 20% difference. So that's what I saw when I compared two algorithms. And I have showed this earlier. Both of them, Kalman filter and hidden Markov model, is very general algorithms that can be used specifically for the sensor data. And actually, when I used it on the sleep stage data, it smoothed it out and then predicted very well. But unfortunately, I did not have the good visualization of it here. I guess I'm done with the talk. If you have any questions, and I hope I didn't bore you much.